Welcome grade 12s to this physical science lesson. My name is Gillian. Today we're going to be looking at the big ideas surrounding electrical circuits. Now you know how big this topic is. Electricity and magnetism consists of electrical circuits and electrodynamics. We just don't have time to do both of those today, so we're going to be focusing on electrical circuits and what we need to know to answer questions. You know most of this information. It comes from the grade 11 syllabus. Temba has put out some amazing teaching videos around this topic. So if you are struggling with the details, go back and look at those videos. They are incredible and they will help you with understanding the detail. So let's have a look at an overview of what we have already known, what we've studied in grade 11. So electricity, we spoke about voltage, current, and resistance. You've already had a look at that. So voltage is another name for it, is potential difference. It has a symbol of V and it is measured in volts. Current is I, it has a symbol of I, and it is measured in amperes. And resistance has a symbol of R, and it is measured in ohms, and it has that interesting little Greek letter that looks like that. That you have spoken about in terms of Ohm's law. Now we will go back into Ohm's law today, because we do need to know the details around Ohm's law. So we're going to head back into Ohm's law. So last year you would have already spoken about two types of circuits, a series circuit and a parallel circuit. In a series circuit, all the components are joined together and the current moves all the way through, and so the current remains constant through that circuit. The thing that is different that changes is the potential difference. So a series circuit is a potential divider. It divides the potential difference. A parallel circuit is different. The parallel circuit, the potential difference across each component remains constant, remains the same, and the current is divided. Okay. Now power you would have discussed in grade 11, their power also relating to Ohm's law, and there would have been a number of formulae that you would have obtained out of that. So we're going to look at power again because it does pop up in your grade 12 exams, and we need to know how to manage those challenges, those questions. So let's have a look at our extension. So we now have a look at types of circuits, and not only the simple series and parallel circuits, but we look at them in combination. So part of the circuit will be in series and another part will have a combination that is in parallel. So we call those combination circuits. We need to be able to apply our knowledge and calculate problems around the combination of circuits. We will look at power again in terms of Ohm's law and how we're going to answer questions around that. And then the other extension, which can be quite a challenge, is this one on voltage or potential difference. And what we do is we break down the potential difference of the circuit and we break it down into the potential difference across the external circuit or the load and the internal resistance of the cell or battery. And we're going to have a look at that in detail. So let's see what we're going to do first. Ohm's law, that is going to be our first big idea. Ohm's law is a definition that you need to know off by heart. There are key words to this. So let's look at it, and then we will look at the understanding behind it. So the potential difference across a conductor is directly proportional to the current in the conductor at a constant temperature. So potential difference across a conductor is directly proportional to the current in the conductor at a constant temperature. So how did you find this relationship? A specific resistor was tested, and an increase in current through the resistor and the resultant potential difference across the resistor was measured. A graph line that was straight was found. So that means that the independent variable was current, that's the independent variable, and the dependent variable then was potential difference. The relationship between the two was found to be directly proportional. So if we draw a little triangle on the graph line, we can find the slope, the gradient. We know that the gradient is change in V over change in I. Okay, so change in Y over change in X, and that was a constant value which was found to be the value of resistance for that particular resistor. We find that if we have a resistor of lower resistance, that we get a gradient which is of a less steep slope. If the resistor is of a higher resistance, then our slope will look like that. Now, this is particularly for those resistors that follow Ohm's law, and they're called ohmic conductors. What about a resistor that doesn't follow Ohm's law? Well, it is called a non-ohmic conductor, and what it will do is it will look as though it is starting to follow Ohm's law, and then all of a sudden it will change tack. It will change its direction, and it's very confusing. But that means that it's starting to misbehave, that it will not follow Ohm's law, and we call it a non-ohmic conductor. Welcome back, grade 12s. We are busy with electrical circuits, and we're now going to have a look at power. Now, power you last saw in grade 11, so we do need to brush up a little bit. So power, how do we define power? Power is a rate. It is how fast. It is about time. And the definition is the rate at which work is done or energy is converted. That is our definition for power. How does it look qualitatively? Now, qualitatively is without specific numbers. So often we see the power that is within a conductor or a resistor. We see it, particularly in a light bulb, we see it as brightness. So brightness. So if we have a light bulb with a high power rating, it means that energy is converted per second fast, very fast. So it's a very bright light bulb. If we have one that has got a low power rating, in other words, let's say it's 20 volts instead of 40 volts, it means that energy is converted at a slower rate per second. and it is going to look dim. So often when we speak about brightness in a challenge or a question, we're speaking about the output of power. Now the power formula is change in work over the change in time. We have discussed already that power is work done or energy converted. Its unit is a watt, and it is joules per second. The symbol for power is a P. You can see there it's a capital P. Now in terms of electricity, power can be given the formula of V times I, which is potential difference times the current. When we use Ohm's law, here we go, Ohm's law, and convert or change around those, the subject of the formula, we from Ohm's law know that the resistance is equal to potential divided by current. We can change it around and we get another two ways of saying Ohm's law, or the formula to represent Ohm's law, and that is I equals V over R, as well as V is equal to IR. And then we can play around a little bit with the formula, and we end up with, if we substitute these formulae into the original, we end up with P equals V squared over R, as well as P equals I squared times R. Those you will find in your data sheet. If we plot graphs of the power versus the potential difference across the conductor or the resistor, we end up with a relationship that looks like that. So P is directly proportional to the square of the potential difference. The same applies for this graph here, which is where we plot power versus the current that is flowing through the conductor, and we end up with a relationship with this, which is P is directly proportional to the square of the current. Those we can use to solve problems. It will be up to you to decide which formula you're going to use to solve the problem, depending on what information has been given to you. So here we have a question just to show how we are being asked to draw in information from this huge pool that we have learned and put it together in a way that makes sense. So here is a question. You can see that the battery or the cell is represented here. It has an internal resistance. You can see it there. It also has a value E, the EMF. Okay, so that's telling you about the maximum amount of energy converted or transferred, supplied to a coulomb of charge. There is a voltmeter that is measuring the potential difference across that cell or battery, and there is an ammeter which is connected in series within the external circuit. We have got a load, there's the load of 5.6 ohms, and there is an open switch. That open switch is telling you that we have got a reading of EMF on the voltmeter. Along with this question is given you a graph. The graph is showing you potential difference on the y-axis versus time, and in the question it tells us that at t equals t1, time equals t1, that is where the switch is closed. So the switch goes from open to closed. That means that charge is now flowing. Define the term EMF of a battery. I've just done that. So look back and see if you can do this without looking, and check your answer. Then write down the value of EMF of the battery. Well, EMF is when the battery is not being taxed, when the switch is still open. And if we look at this graph, we can see it there on the y-axis. It is 13 volts. When the switch S is closed, calculate the current through the resistor R, then the power dissipated in the resistor. So let's move on to that. Power is represented by these three formula. You can use any of them. You would have to calculate the I first, and that's what is being asked in the first question, the current through the resistor. Once you have found I using Ohm's law, you'll find it as 1.88 amperes. So that would be the answer for that question. You're now going to use that answer of I to calculate the power. Again, you need to decide which one you're going to use, which formula you're going to use. And for this particular one, I am going to use P is equal to VI. I will substitute it in, and I get 10.5. Now, why do I get 10.5? I'm going to show you now. My answer here is 19.69 volts. Sorry, watt. If I turn back to my graph, I can see that where the switch is closed, my potential difference drops to 10.5. That is the trick. It becomes a little tricky. So, power, when we're using power in a problem question, we have to be thinking about all the elements that are involved. Grade 12s, please join me on the next lesson when we do a consolidation and we delve into these questions a little bit more deeply. It was great to have you with me. Bye for now.